Recording stopped.
Even this screen is not really sure. Good afternoon, everyone. I'm Dr. Nageswara from the Department of Mechanical Engineering, and welcome to the first of a series of 4 lectures on the science and engineering of mechanics. Our presenter is Professor Peter Eberhard from the Institute of Engineering and Computational Mechanics at the University of Stuttgart. And now I'll take a few moments to introduce, to give you a brief introduction about him. After graduating from the University of Stuttgart with a degree in mechanical engineering, Professor Eberhard worked as a research associate at the University of Stuttgart and as a visiting scientist at Argonne
Recording in
National
progress.
Laboratory, USA, before returning to Stuttgart for his doctoral degree. Subsequently, he has held positions at UC Berkeley, the Friedrich Alexander University in Nuremberg, and currently he is the director and full professor at the Institute of Engineering and Computational Mechanics at the University of Stuttgart. His research interests range from multi-body systems, mechatronics and control, optimization, robotics, biomechanics, and meshless particle systems. He has authored many peer-reviewed publications and books in the field. And now, without further ado, I'll give you Professor Eberhard.
Thank you very much. Thank you very much for the introduction. And thank you very much for joining this lecture, either here in the room or some people are also joining using video meeting with Zoom. So thank you very much. It's really my great pleasure to be here in Moratuva and to give this series of lectures. And also, it's my great pleasure that I can introduce you a little bit what we are doing in Stuttgart, in Germany, and give you an impression how we are doing research and what are our ideas. I was asked to give you first a little bit an overview about the education system in Germany, how does it work with studying at university and so on, until you finally leave the university or stay forever at the university as I'm doing. I will give you some information about this. Soon we'll have here also the talk, but in the first minutes I will not need the slides. I was asking this question, why is dynamics so interesting? And I hope that I will be able to answer you this question and show you many, many applications and many different aspects of dynamics. And this is one of the strengths of engineering, that we are able to work together with other people, with other categories, with other departments, with companies, and so on, to solve demanding problems. And as a person highly involved in teaching, this is for me something very important. We have to educate the students now, which are the industry engineers and the industry leaders of tomorrow. And so it's always a pleasure to see so many young students also here and so many young colleagues who are our future, basically. So the University of Stuttgart and engineering and also education. In Germany, usually the young children go to school at the age of about 6. Then they are staying for about 4 years in elementary school altogether. And after these 4 years, the groups is basically split up. About half of them will go to high school. They will get later their diploma and can continue to university. There are 2 other groups who remain in the school shorter. And so every child in Germany is between 9 and 12 years in school. Of course, some of them fail and then they are 13 or 14 years in school, but the regular thing is 12 years. After this time, you can apply to go to university. And there we have a bachelor-master system. I think very comparable to your system. So we have something like 6 semesters for the bachelor. In reality, students need more, 8 semesters in average, and then a 4-semester master degree after this. During this time, they already specialize, for example, in mechanical engineering, in civil engineering, mathematics, or whatever. And so they get finally their degree, their master degree in mechanical engineering, for example. Many of these students then go to industry, and I will talk about the industry in a moment. Others will stay at the university to continue with a PhD, and in a university like the University of Stuttgart with a large industrial background, we need many, many doctoral students. And so I would say about 30% of our master graduates will continue with PhD studies. The reason is, of course, because it's interesting, but it's also interesting for companies. Germany is a very poor country in a certain sense. We basically have nothing in Germany The only thing we have is people, is the brains of people. We have no natural resources in Germany. We have not so nice weather as you have. We have no ocean, so no possibility for tourism and all this. The only thing is we have people, we have their brains, and they have to work to create the wealth of the country. And so we are very grateful for these people who study hard, who learn a lot, and to continue then in industry. And industry is honoring this with high salaries and interesting topics they are doing. And so in this sense, in Germany, many people continue with doctoral studies compared to some other countries. So Stuttgart is in the southern part of Germany. Many of you will not know Stuttgart, of course. It's a city with about 600,000 inhabitants, so globally seen a small city. But it's the center of a huge industrial area. So all of you know the cars of Daimler, Mercedes-Benz, and so you have seen the fancy sports cars by Porsche. They are all produced in Germany, in Stuttgart area and the surroundings. But we also have many smaller companies. Only specialists will know. For example, Mahle is one example. They produce cylinders for high quality cars. So if you buy an expensive car in the future, then you will very likely have a cylinder by Mahle in your car. Or Bosch semiconductors. So all of you have a mobile phone with them. All the sensors very likely come from Bosch and are produced about 30 kilometers away from Stuttgart. And so we have a huge variety of companies producing things for the world market, and they are really interesting for us. So the University of Stuttgart has about 25,000 students. We are divided into 10 departments. 2 of them are in the mechanical engineering direction, and we only have about 250 professors, which is very few if you compare it with many other countries. But we have large research institutes. One of them is my research institute, which I will present you in a few moments. So the departments of mechanical engineering, there are about 35 institutes. For example, my institute is working on mechanics. There's another institute working on vehicles, another one for laser application, for design, and many more things. So it's one of the top 3 universities in Germany in terms of funded research. Unfortunately, we are never number 1, but we always fight for number 2 position. And it also is among the top 4 universities in Germany in mechanical engineering. So in all the ranking lists, our university, University of Stuttgart, is, I think, at number 350 or so worldwide. But in engineering, we are in the top 80 or so, which is a quite nice position for us. Okay, and I want to present you now what our research institute is doing. Do we have a beamer now? Source protected. Okay, good. So here we are. So I missed that it's one of the oldest technical and engineering universities in Germany. It was founded in 1829. This is the oldest building in our university. In the central part is the office of our president. My institute is the one here below. The 2 top floors are ours. So this is in the modern campus in Stuttgart 5. And these are the working areas of our institute. So it's multi-body dynamics. I will show you examples. It's particles, it's uncertainty, biomechanics, driving safety, and a lot of mechatronics and control. The red names are the names of the people working there in this institute. So you can see everything has to do with dynamics somehow, and I will show you that it's a wide variety of topics we're working. In Germany, there are typically 2 pillars of education and universities important. One is teaching. Of course, teaching is very important for us. I had to count it for some statistics. During my time at the University of Stuttgart, I was responsible for grading about 45 exams, which is a horrible number, of course. Most of the grading was done by teaching assistants and our staff members. But you can imagine that many, many people have to learn about mechanics and dynamics. And so it's one nice pillar of our work. The second pillar is research. I will show you a lot about research we are doing. This is really central for us. We do a lot of basic research, and we want to do a lot of applied research working together with companies. So many of the things you will see is together with companies. And then there's the third pillar, which is a little bit untypical for a basic research institute, and this is industrial corporations. And here you see the logos of some of our industrial partners. There are a few logos which you will recognize. For example, Porsche, the sports cars, Daimler, the big luxury cars. Then there are many you will not recognize. For example, Eurocopter, they are producing helicopters. Or Festool, they are producing drilling machines, handheld drilling machines. G-Truck, it's gear drives for vehicles of all kinds. There are also a few strange things. For example, WMF in the middle, upper part, they are producing cooking pots. And it's really strange. You would think about a cooking pot that it's a very simple device, nothing to optimize, nothing to improve. But we had a huge project with them. Maybe I can show you a little bit the background, why it was interesting. If you want to buy a really expensive stove for your kitchen, then you choose an induction stove. And if you buy this very expensive induction stove, you automatically get a set of pots with it. And the company, of course, they don't give it for free. They ask you for a lot of money. And then you put the cooking pots on the stove, and it starts to vibrate and making noise like this. Of course, you run immediately to the company and say, okay, this is rubbish, it does not work, please exchange it. And so they had tremendous problems with people complaining, your oven is not working nicely, it produces too much noise in our kitchen. Okay, and then the poor company had to solve this problem. And this is one nice thing of cooperation, which happens in our area frequently, that companies try their best to solve problems, and if they are not able to solve it alone, they ask university for assistance. This is very important and very interesting, and certainly also an area Moratuba and Sri Lanka will go to. So companies have to ask the university for advice, and they must be sure that they get good advice and good recommendations by universities. And of course, these companies have to pay for it, and they have to pay not for my salary. I do not earn any dollar for this. No, but they have to pay for our equipment, and they have to pay staff costs and so on. And so both parties have their benefits. For the cooking pots, by the way, the cooking pots were not responsible for the noise. It was the control of the stove. It was pumped, not a smooth transition of the energy flowing into the pots. It was impact-like transition. Okay, and this, as an engineer, you know, if you introduce impacts to a system, this is a very hard excitation, and you will suffer and get disturbances. Okay, this was just one example. Rolls-Royce is not the nice automobiles. This is ship engines in Norway. CRRC is the big Chinese company producing trains, the largest train producing company in the world. So we also have some international partners which are cooperating with us. So this is very important. Here a little bit about the structure of our institute. There are many smaller institutes in our universities. There are a few really big institutes. The largest one has over 200 employees. The smallest one is just the professor and the secretary. So the size is very different. I will show you we are about 40 persons at the moment in our institute. But there are only a few permanent positions, professor positions in the top row, I myself and the other persons. Then there are a few non-permanent positions paid from the state. This makes in total 8. Secretary and the technician makes 10. So where are the other peoples from? And the other people are funded from third party. They are funded from the German Research Council, they are funded from industry, they are funded from European Union, all kinds of different sources of money. So whoever has a problem in engineering, mechanics, can come to us, discuss with us, and if it's interesting for both sides, then we can make a project, and all these people are paid from such money. A few of them are directly cooperating with industry. Most of them have their contracts at the university. Many of them are engineers, but we also have mathematicians. We have 2 employees who studied restoration of art, something completely different from our usual engineering business. And as in the introduction it was already mentioned, after this talk today, where I want to give you a lot of insight what we are doing, very short only, we will have 4 talks, 2 on Thursday, 2 on Thursday in a week, where I want to go in the details and want to show you some more detailed information about various topics. Feel free to also join these talks. You are very welcome. You make me happy. It's also always very nice to see people interested in what we are doing. So I'm very happy if you are here and get some inspiration. You can also see some of the people are not from Germany. There are some from Asia, from China, from Nigeria, from Africa, from Russia, one from the Ukraine, which was a little bit funny because the person from Ukraine and from Russia, they're sitting opposite to each other, desk to desk. And the funny thing was, it was absolutely peaceful. They can distinguish what are the political things and what are the personal things. And we had similar things when a person from Iran was sitting opposite to a person from Israel. Also a lot of potential for conflict. But this is something we really want to have at the Institute. We want to work together in a very trustful and peaceful environment. So no problems in this direction. Okay, now I want to go through many of these projects to give you an impression why is dynamics interesting and where is it used and how do we approach it. One thing here, for example, Michael Hans, one of the associate professors of our institute and the vice director of our institute, he is doing vibrations. You can hear it. Of course, you can imagine if you do experiments with this kind of noise, you are the best friend of all the other people in the laboratory. So it's horrible. This is brake squeal. If you buy an expensive car and press the brake, you do not want to hear any noise. Unfortunately, brakes will produce noise. And again, the people complain, call the company, you have brought us, sold us a car which is damaged. Change it, do something. And then the problem must be solved. And therefore, these companies work a lot how to remove all the noise from brakes. This is a project going on for many years, more than 10 years now, together with Porsche to reduce brake noise for these high quality sports cars. But Michael is also doing uncertainties. Usually when you are doing simulations, you select one set of parameters and then you do the simulation, you know the behavior of the system. But what happens if the parameter is slightly changed? For example, if the heat is going up, you all know mechanical parameters are changing with heat. Is the system still working well or is it not working so well? This is something called uncertainties. Some modifications you cannot judge in advance, and then you want to see what is the effect of this. Is it critical? Is it not critical? If it's not critical, maybe you even can relieve the tolerances for production. If it's critical, you must be very picky that everything is perfectly held. And sometimes it goes against the intuition. So there is a famous example, very, very old example. A German company produced in Iran ultra-centrifuges for separating some nuclear material also. Of course, today it's maybe not the brightest idea to do something like this in Iran, because maybe something like this can also be used for nuclear bombs also. Horrible. But okay, it was just an engineering question. And then everything was set up, everything was working, and then somebody in the company had a bright idea. Let's put in some oil which has a lower viscosity. If the viscosity is lower, you need less energy, it's rotating faster, everything is beautiful. But suddenly this was a very sensitive parameter. Adding this oil with the lower viscosity completely damaged the centrifuges, and within a few days all the centrifuges were damaged. Which is good for peace, but not so good for the company which want to produce these things. And so, in this sense, be sure to use the right parameters and know what is happening if something is changing a little bit. And this is done with uncertainty methods. Or Pascal Ziegler is doing a lot of vibrations too. It's about the dynamics of paintings and pieces of art. I will give a talk about this later, where you can see what art has to do with engineering. Just a brief message. If you, for example, transport a piece of art and it's exposed to too large vibrations, you will damage it. And if you damage something, if I let fall this remote control, okay, we have to buy a new one. This is not a big damage. But if you damage a piece of art which is there for 1,000 years and it's only one of its kind in the world, then something is really bad. And so you have to take care of this, and a lot of engineering is there, and I will show you in this talk how we approach this, what can we do with measurements, with simulations, with corporations, with museums and companies. So I'm very glad in 2.5 weeks I will be able to go back to Germany without problems. We had 2 months ago a big project where a very expensive painting has to be transported from one museum to another one, about 200 kilometers difference. And this painting is 500 years old and about 3 meters long, 2 meters high, and only about 3 millimeters thick, a wooden board. So you can imagine if you move it a little bit, the paint will break down. Horrible. So I'm really glad we did this transportation. The painting survived. It's now very nicely arrived at the new museum. If it not arrived well, you maybe would have been able to read everywhere in the newspapers, German professors destroying famous paintings. And then maybe I would have to stay here, never be allowed again to go to Germany. But the transport was okay. Or also a little bit strange left that we can simply buy it. But why are they so expensive, and why is their sound so beautiful that it's better to play on this 250-year-old instrument, the violin, instead of buying the most expensive new one you will find in a shop. And so there are many things. I will also show you something like this. In the middle you see, for example, an X-ray. No, it's not an X-ray, it's a tomography picture. So we did in one of our hospitals. Usually these are very expensive devices to look, for example, into the brain of people or into the internal of the body. But we wanted to look in the internal thing of an expensive old guitar. Okay, so we called the hospital. We have a patient for you. Do you have time? Oh, no, it's not sensitive. It's just wood. So after some discussions, they allowed us to use their expensive machine to get these pictures of this internal of this famous guitar here. But I will present you later the details. Okay. Sorry, this was the wrong thing. Jörg Fehr, he works in driving safety. He's a professor in our institute working in driving safety. And for example, he's interested in airbags, seat belts, and this kind of things, and modeling the human behavior in a car if there is an accident. And it's remarkable what was done. If you look at maybe 20, 30, 40 years ago, many people died from car accidents. Today, the situation is much improved. Not so many people are dying anymore. And this is because driving safety needs so tremendous effort and also improvements. Of course, if we want to do something, we have to model it, we have to simulate it, we have to make experiments, and only if all these fit together with reality, then we can change something in the reality. So this is something which basically goes through many, many of the things I will show you in the next hour or so. Then we have projects with particles. Particles sounds boring. Okay, particle, little balls, and what to do with them. I will show you some applications, what we can do. And it was interesting. This is Dr. Hofmeister-Kraut. She's the Minister of Economic Affairs, so a high politician in Germany. And she was very interested in these particle methods, which was very interesting for us. So she also visited us several times. Was interested in all the explanations. One of the co-workers is here standing beside her, Chantamuli Ganansambantam is from southern India, also came to us after his master degree and made his PhD in our institute. And what are these particles about? With particles, you can simulate many things which you cannot simulate with other methods. For example, this is about friction stir welding. With friction stir welding, you press a tool to a workpiece, and then you rotate this tool under very high pressure. If the pressure is very high, the temperature is going up, and the material is softening. It's not melting. If it's melting, then it's welding. This is another thing. I will come to this. No, it's softening this material, and then you smear the material into each other. The nice advantage is that the seam weld is of extremely high quality. It's very, very stable. You use something like this very often, for example, for planes, for aeronautical industries. And so you want to simulate in one simulation environment the mechanical behavior, the thermal behavior, and many more things. And this is complicated. Or here, laser welding. What is the idea behind laser welding? You direct a laser ray with high energy to a surface of material, and then the surface is melting. The material is melting. And then you move the laser ray. When the heat is going away, what is happening with the melt? It's solidifying again. Okay, and then you have a nice weld. If you do a lot of energy, then you get a deep capillary. It's even vaporizing. The material is vaporizing and vanishing. If you do less energy, it's a flatter weld. So a very interesting simulation again. And again, we use particle methods, smooth particle hydrodynamics, to be more specific, which is a method which is also frequently used in fluid dynamics. Basically the same thing you do in fluid dynamics as you do here for this thing. And the beautiful thing is you can, in one simulation, you can at the same time simulate the liquid, the molten material, and the solid, the not molten material. And this is very interesting, and include all the phase transitions back and forth. Or another thing you can do with particles. This is deep hole drilling. Sometimes you want to drill holes with very thin diameters. This goes down up to 0.6 millimeters, half a millimeter about, very, 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 very thin, and about this height. You can imagine you take a toothpick and then you want to drill a hole in very, very hard metal material. You really have to understand what you are doing. And it's getting more complicated. In this half a millimeter drill, you need cooling liquid. Therefore, in the interior, it's hollow and you are pumping cooling liquid to this very thin tool to the very front. And at the very front, you need it for cooling, you need it for lubrication, and you need it to wash away the chips, which are created. Again, very complicated simulations. Our most demanding ones run on a parallel computer for about 5 months. 5 months you have to wait for a result, which is of course interesting for a doctoral student. Usually a doctoral student is making his thesis with us in 4 to 5 years. So you cannot afford to make too many wrong simulations, because you wait for a result and after 5 years, after 5 months you see, oh no, it has not worked, something is wrong, electricity was failing, whatever. And this really requires you to work carefully. Of course, my co-workers are doing all kinds of tricks. For example, every day or so they save the state, that they have a restart possibility if electricity is going down, and many more things you have to do. But suddenly, it's not just a simple simulation where you run it and within a few seconds you get the result. Suddenly you have to wait for 5 months for a result. But fortunately, not all of these things are so complicated. This is another thing, a very complicated drilling tool. For example, if the surface of the interior surface of this borehole must be very, very smooth, then you can imagine if the chips are on the outside of the driller, they are rubbing on the surface and they are damaging the surface. So therefore, you need special tools where in the interior of the tools, all the chips are fed back. Again, a lot of simulation, a lot of modeling, a lot of experiments. Fortunately, we work together with our machine tool people, and they even can use high-speed cameras to make video recordings of the process so that we can see what is the same between experiment and simulation and what is different. We have to adjust our simulation. Or something very interesting are particle dampers. this coworker here not always has this kind of hairstyle. This was his COVID hairstyle, and we all were not allowed for about 5 months to go to the hair cutter. So this was from this time when we made this photo. So today his hair is shorter also again. It was a very strange time for all of us, I think here, the same as in Germany. For several, 2-3 months we were not allowed to go to our laboratories. Then for 2 more years we were only allowed to go with a mask and so on. So very strange time of our professional life. Yeah, Andreas is not only wearing strange hairs, but he's doing research about particle dampers. If you want to reduce vibrations, you can either use tuned mass dampers, which are very nice, but for tuned mass dampers you damp only a certain frequency. If you know you have a problem with, for example, 50 Hertz, then you can make a nice tuned mass damper, removing most of the vibrations for 50 Hertz. The 50 Hertz in Germany is a little bit infamous because a lot of electricity goes with 50 Hertz or 60 Hertz, and so some of the excitation from electromotors are in this range. So therefore, when we see 50, 60 Hertz, we always think, no, this is electrical engineering. Now what can we do? But if you know the frequency, then you can make a tuned mass damper. But what happens if the frequency is changing all the time? Or if you have many frequencies in your system, what can you do there? And and particle dampers are a very, very nice way of doing this. The concept is simple. You take a container, you fill in particles, and you clamp it to the structure you want to damp. And if you did everything right, the vibrations will go down. You can improve it further. For example, you can enter some liquid, or you can do some other things to improve it. And this is a very nice way of reducing vibrations in such systems. Again, you need many simulations, you need modeling, you need experiments. All this must go together. Okay, here the next are 2-3 projects related to magnetic levitation drains. This is another thing which sounds as if it's not possible to do. If you take 2 magnets and press them together, what can you do? If you're at north to south pole, they are attracting each other, or if you rotate it, then they are trying to get away from each other. Simple. Now, the same thing can be done, of course, with a vehicle. You can set a vehicle to a rail, place some magnets there, and if they are repelling, then this vehicle is levitating. It has no contact anymore to the rail. Of course, it's not that simple. It's a very complicated effect. But if you do it right, you can even build trains with it. A prototype was running in Germany for many years, and also in Shanghai at the Pudong airport, you can see such a levitating train connecting the airport with the city center. Of course, the advantages are obvious. If there is no contact, there cannot be any wear. If there is no contact, there is no friction. Therefore, you can reach very high speeds. The train in Shanghai goes 450 kilometers per hour. But the technology behind is really demanding. So, for example, as I mentioned, this example with the magnets which are repelling each other. In your labs, maybe you have seen the magnetic lines. You can see this if you have metal powder and the magnets, and then they are oriented, the metal powder is oriented along the magnetic lines. And now if you do this, this looks good, but it is horrible, because the magnetic field is all over the place. There is a Japanese system also making a levitating train. They use this concept. And you are not allowed to go close to this train if you have, for example, an electric machine here to control your heart, because this electric machine is damaged. Or if you take your mobile phone to this train, there's a certain chance that it will be completely destroyed after, or a hard drive in the computer is formatted afterwards. So not really nice. So the Japanese have wonderful engineers, of course, they solve this problem, but they need, for example, special entrances to these trains, that everything is isolated and so on. The German system is different. The German system is an attractive system. This means there is the rail and the train is grabbing around and is attracted to the top. This is by itself an unstable system. If you switch off the electricity, the train will fall down. And therefore you need to control it. it's very sophisticated control you need to do, and you need to do this control very fast. A Chinese company, CRC, is building a train with 600 kilometers per hour. Just imagine, 600 kilometers per hour. This is like an airplane, nearly. And you have to do the control for a train riding 600 kilometers per hour. This is truly impressive. And we are very happy that we were selected to do a lot of the modeling of the train and to propose the control of this train as the only foreign partner of this company and the only university partner. Again, you do a lot of modeling, a lot of simulation, and a lot of discussion what is done right. For example, Patrick Schmid here was responsible for control, and he is using NPC control, model predictive control. Those of you familiar with control know NPC is a really interesting, completely new control concept. Some people a few years ago doubted whether you can use it for an industrial system. We use it for these magnetically levitating trains, because all simple control concepts we learned in our university education simply failed. They simply cannot be used. You need high-level methods, and if you want to apply high-level methods, you have to understand them, and you have to do research about these things. So you can see we are not interested in the simple solutions. The companies are better in simple solutions. We are interested what can we do if it's really getting complicated. Yeah, here you can see a picture of the train. This is a German train. Unfortunately, it looks not good. The Chinese one looks much faster than this one here. The reason is also the aerodynamics. The aerodynamic resistance is going to the third power with the velocity. Therefore, if you increase the velocity, the resistance, the air resistance is tremendously increased. And therefore, you really have to make it optimal for all the aerodynamics. And this is what this Chinese company can really do in a beautiful way. And it looks much nicer, of course, also. Here, again, brakes wheels. Here you can see such an automotive brake. And you need a very precise model to do this. And then suddenly there is a phone call, okay, now you investigated in the last years steel brakes, but now we have ceramics brakes. Is it the same? Of course, it's not the same. For example, cooling is not as important as for a steel brake. And then you have to redo everything. You have to investigate the transfer functions very strongly. You have to find out what is critical, what is not critical. These things are done together with Bosch and also partially with Daimler. Okay. This morning I heard that you're also interested in robots and robot swarms. We are also investigating robots. We are also building robots ourselves. And especially interesting for us is again high-level control of robotics. Not the simple ones, but what can we do if the situation becomes complicated? For example, in the lower video, these four robots, they have an acrylic plate on them, and they should transport this plate together. And if they go too fast, the plate will fall down and will be damaged. And so they have to synchronize without external control. They have to discuss with them, okay, now I move there, then I can go there, and so on. And all this must be done in a systematic way. And they also do more complicated things like pushing these elements around, going the way through a complicated maze and all these things. A lot of control theory is behind. Then you need to know what is, if you have uncertainties. So for example, when we do experiments in our laboratory, we can do an experiment now in the afternoon. In the afternoon, the sun was shining, and then everything is a little bit hot. If we try to repeat the experiment in the morning, then parameters are different. The results will not be the same. And if the cleaning woman comes and tries to make everything very clean and nice, even worse, then we can throw away all the previous results. So there are a lot of uncertainties, especially whenever it comes to contact and friction. And then you need methods how to deal with uncertainties, how to run such robots in a safe way. Or here, for example, with many self-designed robots, there was a kind of parking problem interesting for us. So if you have a car and you want to park backward, then you look carefully and you know how to rotate your wheel, and you will be able to do it. Now, if you have a hanger behind, then it's quite hopeless. At least for me, it's quite hopeless. Because this hanger adds a lot of dynamics and complexity. Of course, an experienced truck driver knows what to do, and then he can even pulp with a hanger. But what happens if there are two hangers? Then I'm absolutely convinced that there is not a single truck driver in the world who can do this just by experience. It's too complicated. But with a lot of interesting control, you can solve such problems. And this becomes more and more interesting because people want to go autonomous. At the moment, a typical truck on a highway is either just a truck or a truck and one hanger, of course. But in the future, maybe you want to use driverless trucks. One truck is driving, there are 10 hangers behind, and then this truck must drive safely in the city, and it must bring everything to the right place, and then you suddenly need a lot of these things. And no wonder that many of the companies, of the automotive companies, spend a lot of money for these autonomous systems. We build most of our robots ourselves. We have something like 20 different robots, or 20 robots of different kinds, flying ones, driving on the ground, so that we have full control about the electronical part and the sensors and everything. A lot of work, some money involved, but we are very happy with these kind of things. Or here a handover problem. A drone is flying and a robot is driving on the ground. They have no connection. The drone can only look through the camera where it's moving. And then it needs to make a prediction. Where is the driving robot going to? And then it has to adjust its trajectory to approach. And then it must be a very smooth transition to pick up something between this moving robot and the flying robot. And again, many experiments, many simulations involved here. Again, same area, a lot of mathematics for these pickup procedures. If you do swarm robotics, another interesting thing is we always assume that the robots are cooperating. But what happens if one of the robots is damaged? If the complete electricity is gone, okay, you will see it. The robot will stand there and do nothing. But what happens if the sensors are slightly damaged and give you wrong results? So the robot wants to do something right, but always has the wrong thing to do, or one of the motors is slightly damaged. Or even worse, what do you do if one of the components in your swarm is not cooperating? If one of the components wants to do something completely different, maybe it wants to sabotage the whole behavior also. How can you identify destructive behavior and correct behavior? It's not so simple. Because if you want to make a damage to something, of course there are obvious ways to do damage. I'm not an expert in making damage, but I think people think a lot, how can I do damage without showing it that I'm responsible for doing something wrong? And these are the worst things. How can you identify somebody who wants to do something wrong and wants to do damage, who wants to hide this? And this is something you can do with we applied for robot swarms, but this is machine learning. For example, here Ingeborg Wenger, she studied computer science and is doing now these kind of things in our institute. Neural networks, machine learning, all these things are involved here. Or intelligent design assistance for flexible multi-body systems is another interesting thing. We know more or less how to design a certain system. But the way we design a system today is very similar how also 20 years ago a system was designed. The big change is that a lot of simulation is added now. This was my generation who added a lot of simulation. But what your generation is adding, I mean the students now, what is what the students are adding to designing systems? I'm sure there will be a lot of machine intelligence behind. You will have many, many choices, and your computer will help you to select the right things. So design 30 years ago was different from design today, and it will be different from design in 20 years. I hope that I will live long enough to see what it is then in 20, 30 years. We have a big national research program. I'm coordinator of this research program. There are about 20 research groups distributed all over Germany who work on these kind of things. What do we have to change in design to prepare for the future? Very interesting. some groups from computer science, from mathematics, from engineering, of course. Of course, the ones from engineering are the most important ones. But all this interaction between the different communities is important here. As a coordinator, it's not always fun to coordinate such a diverse group of people, but we think it's worth to do it, and we think it's worth to investigate such things. Here it's a pelican robot. If you watch birds, sometimes birds fly in a formation. Often it's a V-shaped formation. Of course, the birds must have a motivation. They are not stupid, okay, I follow this one here and then a V-shape occurs. No, they have a motivation. And this motivation is very, very likely energy saving. If you fly behind another robot under a certain angle with a certain height, then you can save energy. And maybe some of you are familiar with cycling, with bike racing. You can watch there very frequently, it's called a Belgian gyroscope, a group of people doing bicycle racing. They drive one after the other. Of course, one is driving in the so-called wind shadow of the other, saving a lot of energy. And then after a few minutes, this person is just going to the side, the next one has to go. And so the person going to the side goes back, and at the very end he's sorting. And so this group of maybe 8, 10 people can go very, very fast. Why? Because they are sharing. And always the first one, he has to take the wind. This is the person who has to spend a lot of energy. And so by changing this again and again, they save a lot of energy for the bike racing. And interesting, pelicans do the same. Of course, nature is very clever, and over the years, they invented this also. So the front pelican, it's not always the front pelican. They are changing, and then the front pelican is leaving, sorting in, going to the back, and moving. I saw here in the lake some pelicans. I not saw a pelican swarm, unfortunately, but I think I have to watch carefully. I never saw a swarm of pelicans in nature, only in videos, unfortunately. Now here a project where also Aruna Disanayaka, one of the graduates of University of Moratuva, who joined our institute a few years ago, contributed a lot. This is about the coupling of optical methods and mechanical methods. And what is the problem? If you have a complicated lens system, you get a precise image, and you can use it, for example, for chip production. If something is changing slightly, the chips will be damaged and you can throw them away. To give you an impression what it is about, for traditional machines like for chip production, the optical system has a diameter of about this width, maybe 50 centimeters, a height of about 1 meter 50 or so. And it's the same as the optical system in your camera, just better, more expensive, bigger. Such an objective costs something like 2 million euro, a very expensive thing. And now these things are used to create chips. And now imagine if I hold my hand here and the heat from my hand to your face, for example, is about 2 meters, is sufficient if this heat is going to this big optical system to bend it a little bit, and if it's bent a little bit, the optical system is disturbed and you can throw away the chips. Just from the hand, just this little bit of heat is sufficient to destroy the chips. And this is a device with a weight of, let's say, 400 kilograms, 500 kilograms. Just this little energy is sufficient. So therefore, you are at the absolute limits of physics. By the way, modern chips are not always produced in this way. Why? You want to make the structures smaller and smaller and smaller. But there's a physical limitation. If you want to make the structures smaller, you want to make the wavelengths of the light smaller, which are used. Therefore, you go from red light to violet light and so on. But if you further reduce the wavelength of the light, suddenly glass is not transparent anymore. So if you look through this glass, it's transparent, I can look outside. But if you want to send a ray of ultraviolet light to this, it's blocked, it cannot pass. Therefore, lens systems are not possible anymore. Therefore, you have to switch to mirror systems, where the ray is reflected back and forth. The precision, again, incredible. These lenses are freely floating in vacuum, They are only held by electromagnetic fields at their position. And if you direct a ray on this mirror and send it all the way to the moon, a deviation of 1 centimeter on the moon means your chip is destroyed. Incredible. And so you need a lot of control, a lot of mechanics, a lot of thermodynamics to investigate such systems. And I will show you also in one of the talks what has been done there. Aruna was involved in setting up one of the experiments and setting up the hardware. By the way, we were very happy with his work. He was very well educated in your university in mathematics, in signal processing, but also in these hardware things. So this was very interesting to see what he was doing. So I always recommend really took a lot of care for the foundations. If you know a lot about mathematics, you will need it all your lifetime as engineer, and nobody can take this away. If you're only familiar with a certain machine, in 5 years a new machine will come and all your knowledge is basically old-fashioned. So therefore, go to the foundations, and if you have a strong foundation as an engineer, then you can solve all the problems. If you have only very specific knowledge, okay, then you can use this specific knowledge, but not more. So foundations are so incredibly important, and we were very happy with his foundations, which helped us a lot. I already mentioned this project with the guitars, a lot of simulation, experiments, also guitar making. We're working together with guitar makers from Italy, how to produce better guitars, how to investigate all the strings and all this, many things. This is about this behavior of paintings. Again, you need a lot of detailed information about this. So for example, when sometimes you look at such an old painting, you get the impression, oh God, this is damaged, horrible, because the paint is broken, and then the layer is sometimes moved, and so there is a certain movement like this. And so as an engineer, you first think, oh, horrible, it's broken, it's damaged, let us throw it away, or let us spend a lot of money to repair it. But this is not so critical. But what is really critical, if you can see effects like this, where the paint is moving up, then you know, okay, here are now stresses and strains, and this is soon breaking up, so you have to avoid that this is breaking, because this can break and create a lot of damage. And so we have to know in such paintings what are critical situations and what are not critical situations. One reason why this is interesting is money. At the moment, many expensive pieces of art are moved around between museums. They are borrowed from one museum to the next museum, and this makes a lot of sense. For example, a certain museum wants to show as many as possible pictures of the famous painter Van Gogh. And then they do not have all them in their own collection, so they ask another museum, oh, can you borrow us the picture? If somebody wants to borrow a book from me, I tell him yes. If somebody wants to borrow a painting which is 200 years old and millions worth, then I will say no. Okay, if you still want to borrow it, you need an insurance company which is willing to make sure if something is damaged, it's at least repaired and paid for and so on. And so a lot of this money goes to insurance fees. And the insurances want to know precisely how dangerous is it for a certain piece of art to be transported. Is it safe, more or less, or is it a high risk? And I'm absolutely sure, for example, nobody would dare to, no company would dare to make an insurance for the Mona Lisa in France in the Louvre. If something is damaged there, well, nobody can pay it. And so there are a few things where nobody can pay it, others are still possible, but you need a lot of information. I will give you a lot of insight into this art in one of the next talks. And here also one of these art conservators, she studied at our art university in Stuttgart, and so she knows everything about paint and the fabric below and all this, and so it's very helpful to have Eva in our team. This is a project about model order reduction. This is mathematics, how to make a big system small. I'm sure many of you have worked with finite element codes. If you make a finite element model, you have all these small elements connected at the nodes and all having deformations, and then you run into very big systems. For example, we had a nice problem with Daimler. It was about the behavior of a seat in a car. And this model had something like 3, 4, 5 million degrees of freedom. So every single matrix was 5 million by 5 million. This is a huge matrix. And now the question is, if you want to make a long simulation, how can you do it? You cannot make a simulation, for example, a car driving 100 kilometers for a 5 million times 5 million matrix. Too large, too impossible. Therefore, you want to reduce it and want to make sure that all the relevant information is still included. This is the purpose of model order reduction. Mathematical methods how to do this. For Daimler, it was interesting. These companies sometimes have strange concepts behind. For Daimler, they have one very important criterion. They have been founded in Stuttgart area and have their big factories in Stuttgart. And there is Ulm, a little town about 100 kilometers away from us. And so every car they build, every prototype, they equip many, many sensors, and then they drive exactly the same street all the way to Ulm. And because they've done this a few thousand times, they have all the measurements, and then they can say precisely, okay, this is a good car, this is not such a good car. And of course, 100 kilometers drive means 1.5 hours or 1 hour or so. And this means a long, long simulation if you first want to simulate it. And this was one of the reasons why they were so interested in reduced matrices. Other companies have other measures. For example, in Germany there's a famous racing track, the Nürburgring racing track. The Formula One enthusiasts know it. In the past, it was the most important racing track in the world. Now it's not safe enough, so it's not used for Formula One racing anymore. But Porsche has the simple criterion. Whatever car we build, in his category, it must be the fastest one on the Nürburgring. So if there is another sports car, a Lamborghini or whatever, faster, then the engineers are sent back into their offices. No, this car cannot be called a Porsche car. It's not the fastest on a Nürburgring, so forget about this car. We will not sell it to anybody. So a simple criterion, the complete quality of the riding quality of the car is suddenly in one number, the lap time on this racing track. A very strange thing, but companies need this information. If you want to provide them 10,000 numbers, some are better, some are worse. Okay, nobody knows how to compare 10,000 numbers. But if it's just one number, okay, they will know. And you can imagine that they know a lot about their other cars. Just to give you again an example, I was asked to tell a little bit about companies and universities in Stuttgart, so therefore I'm telling you these kind of stories. When you visit the Porsche factory close to Stuttgart, they have a Mensa where all the people can eat in the afternoon, and in the front of the Mensa there's a big room, maybe 1.5 times this size of this room here, and from time to time they disassemble a competitor car and they place all the parts on the floor. So that everybody who wants to go to have lunch has to pass this car, and then they can see, okay, oh, this is the part, how are they doing this? Oh, why are we doing it differently? And you can learn a lot of this information. So if you're in the position later to sell one of these high quality cars to Porsche, it's very likely that it's completely disassembled and ends in front of the restaurant of Porsche, where it's investigated carefully. Of course, the other companies do the same, so it's fair, it's not a criminal competition or so, but it's interesting to see the car. Of course, as an engineer, it hurts a little bit if you see, oh, this car has cost 200,000 euro and now it's completely destroyed, all this on the floor. But they think it's worth to do it. I guess later they will assemble it again. At least I hope so, at least. I hope so. And I hope that all parts are still there on the floor, that they can assemble it again. This model order reduction is also important for simulating helicopters. This is a project together with Airbus Helicopters. They're producing helicopters, of course, it's in the name. And in helicopters, there are two sources of disturbance. One is the rotating blade, like the ventilator here, and the other are vibrations in the cell. If you want to ride such a helicopter and want to control such a helicopter, the disturbances are so strong if you are not really actively do something that the pilot is not able to hold the steering stick in his hand. It's shaking like crazy. And therefore, you have to damp out these vibrations. Thank you. You have to damp out, reduce these vibrations highly. And therefore, you need the interaction between the airflow, between the structural vibrations and all this. And suddenly, you have to do a lot of mechanics and simulations behind. And then planes are usually very standardized. If Boeing or Airbus are producing a certain plane, then this plane looks more or less the same for all customers. Helicopters are very different. Every helicopter is a little bit different. One is for the police, one is for a rescue team, one is for a rescue team in the mountains. And so the equipment and everything is different, and so are the mechanical properties of such a helicopter. So beautiful for us. I always enjoy if companies have problems, because then they have to come to the university and cooperate with us. Of course, the companies not enjoy it so much to have problems, but there's a certain sense of cooperation which developed, and this is very important and something which is also, of course, developing in your university and must be strongly promoted with local industries here. This is about electromotors. There are these rare earth materials which are a big problem because there are only very few countries which have them in their ground. The most important one is China. Nobody knows when China suddenly not sells these materials anymore. So we need to be prepared for this. We do not have them in Germany, of course. As I told you, we only have brains, we only have people. So therefore, industry is working strongly how to make electromotors without these special materials. Neodymium, you all know it from magnets, for example, is one of these bad materials, which is so rare and unfortunately all below the earth in China. There are also a few other countries which have it, and a few clever ideas where you can get it from. This is something in biomechanics, also something you usually would not expect in a mechanics or in a mechanical engineering. Here you can see the ear. The ear is a wonderful mechanical system. There is, if you look from the outside, there is a tube. Then there is the eardrum. It's just a mechanical membrane, like the one you learned in your undergraduate lectures. Connected to this membrane are three little bones. These are rigid bodies. The rigid bodies are connected by some clever joints. And then the vibration is going via this staples here to the interior of the ear. This is a liquid-filled coil, liquid-filled fluid mechanics. And in this liquid-filled coils there are air cells which are excited, and the air cells give you the signal to the brain. Wonderful. Wonderful if it works, very bad if it not works. So for example, if you have an inflammation in your inner ear, basically it's gone. Then nobody can repair an inner ear. This is really so sensitive. This is a very big problem. Other things can be repaired. For example, problems with the bones here can be repaired. Or here the eardrum is not really that difficult to deal with. This is very can easily repaired by medical doctors. But now people have sometimes very serious problems, and then they make prosthesis. Either active prosthesis, which are little electromotors in the ear, or passive prosthesis, and you have to design them. And fortunately, medical doctors cannot design it because they have no background in engineering. And so you have to work with these guys from engineering and from medical systems and from those who produce these kind of things. Very, very interesting. And also sometimes a little bit strange because we as engineers, we have a different way of working. We think hard about the problem, then we do some modeling, and then we do some simulation, and we redo everything because we really want to be sure these are humans behind. And then we do it a third time to be really, really sure. And then finally we make a proposal. Maybe you should change this and this. But be very, very careful, we tell to the medical doctors. Medical doctors are different. They try to play around, I would say. And so we had situations where we told them, okay, we guess that if you change this, it will help you. And then they told us, yeah, you're right, we just already tried it to our patient. And then sometimes you hear, okay, it worked. Sometimes you hear, no, it's not working. but then also a person is behind. So interesting to work together with people with different cultures, also in terms of education and background. Okay, you are already. You just tell me if I should switch on or do whatever. I already talked about these uncertainties in systems, which is another interesting topic for us, and several co-workers are working on this. Oh, my screen is working. But I can also talk a little bit about the next slides without showing you the pictures and videos. They will come in a moment, I'm sure. Another thing is driving safety. For example, there's a lot of work done for cars. We have all these airbags, seat belts, all these kind of devices in our cars. Sometimes even at the side there are additional airbags. On the top there are additional airbags. I'm not sure whether I want to be in a car if suddenly 5 airbags are exploding. It's really horrible if you see in such a company the sound and it's incredible. It is an explosion and it feels like an explosion, but of course it saves life. But what about motorbikes? Motorbikes are basically unprotected, and the worst thing is if there's an accident and the driver is leaving the motorbike and is flying around. So therefore, there are new ideas. Detected. Okay. Getting closer again. Oops. Yeah, here it is again. So this is such a motorbike accident with protection. The previous situation was without protection. And so one is trying to make seat belts for the bike drivers and also airbags for the bike riders. This would highly protect them and would keep them on the bike. Again, some projects together with companies, but it makes a lot of sense. Just imagine this accident. Nobody will survive such an accident. The other situation, this can hopefully be survived by people. And for this reason, of course, we need, again, volunteer tests, which is a bit difficult, driving simulators, simulation models, behavior of all the muscles and so on, and also a lot of analysis of simulation data with machine learning and other aspects. I want to be a little bit faster here, again coupling all this with reduced order models, and also for autonomous driving we need a lot of things. At the moment, if you drive a car, then the driver is sitting behind the steering wheel. And if you have another person sitting beside you, then this person is sitting in a well-defined position. But in the future, this will change. There will not be a steering wheel anymore. And so maybe when you go to work in the morning, you just go to your car, take a nap, sleep in your car. And this is, of course, a serious issue because you are not in a well-defined position anymore. But if there is an accident, you still want to be protected. But how to design, for example, a seat belt for a person which is laying in his car and not paying attention to the traffic anymore. So these are interesting things to also investigated together with companies. Then here, one project together with the company, this is digital twins in production. Production engineering is very good in producing colorful pictures and videos, but sometimes the physics behind is not so good. And so they really want to combine high-level control, hardware control even, sophisticated mechanical models, visualization, animation, couple all this with the real plant, for example, running the real plant over the distance. This is really sophisticated things. For example, I had 1 year ago or so, I had a person from Rolls-Royce company in my office. They're producing ship engines, and then he showed me some measurements. They were moving, and then he showed me, okay, this is now a ship driving along before Ghana, so in Africa. And here you can see how the engine is working, and it was possible to see every single hit in the gears in the engine of this ship. So these ships are monitored from Norway somewhere. There's a big room where all the information is coming together, and then they can tell these people, oh, now be very careful, your engine might break in 100 kilometers. Be really careful with your engine. And this is something also very interesting and requires a lot from us engineers. Okay, the last slide before I leave is from Kaluka. He's investigating milling processes and fancy tools for producing milling. So you all know straight fluted milling tools, but then you can make helix tools, which are already much better when it comes to chatter and vibration suppression. But they can do more. You can get a kind of wavy signal on the tool and further reduce vibrations. And Abraham is investigating these kind of things. Okay, let me come to a few final remarks. I tried to show you that engineering is such a wide field, that there are so many interesting problems behind. And again, especially the young among you, there are so many things for you in the future to do. So you definitely selected the wrong education and the right job. It's never boring, and this is what I really want to have for my job. I want to be excited from morning to the evening, and from the age of 25 until the age of 68 when I have to retire. And this is something you not get in too many other jobs. But engineering is one of these jobs. And so congratulations, you made the right decision for your own professional career. And then be open. There are so many interesting things to do, and so many things where you and as an engineer can contribute. And this is important, that you can contribute something. You can provide important information, important knowledge, important background. And this is so interesting, because in the future it's not as it was in the past that you learn as a mechanical engineer and do nothing else. In the future we will also have to deal with electrical devices, with optical devices, with a lot of computer science and programming, and all this is in your education, and so use it wisely. Now, a very last comment. As it was mentioned, I will be here for the next about 2 weeks. So you are very, very welcome to just come to my office and to contact me. I would recommend just send me an email before you come. Here is the email address again, so that we can make an appointment. And then feel free, if you want to just talk a little bit about what we are doing in Germany, about what my institute is doing, maybe also what is interesting for you in the future, what you can do there. And then just talk about this. It will be interesting for me. Just imagine if I sit there for 2 weeks without talking to anybody, how boring this would be. So I really appreciate seeing you again. Okay, thank you very much for your attention. Are there any questions, any comments? Don't be shy. This is an interesting effect also in our lectures in Germany. Sometimes there's a lecture hall with 800 students, and you ask a question and suddenly 800 students are so it's the same.
How these for engineering students. Maybe management students are different.
Yeah, 800 of them will even talk to you even before you ask the question. I know. And my wife studied, she's teacher, she studied education. These guys will not even come to the lecture hall. They all will sit in the cafeteria and talk to each other from morning to evening. So very different culture behind. Very interesting, different cultures. Okay, so thank you.
Yeah, how do you use the industry project in the academic process? You talk about how you use that from industry in the project, but how do you use that academic?
This is something we definitely should talk a little bit about because our goal is completely different. When the companies have different kind of projects in their mind, when we ask them, please give us an undergraduate project just to make a little bit contact between the company and the university, they always provide boring projects. Some things they not really need. They think, okay, let's just do them, let's play around, not so important. No, we want to work with the real problems they have, and therefore we always tell them, if you do a project with us, then our engineers, our staff members will work on this, and they will use also students to work on it. But there's also one of our co-workers who is kind of supervising this and who is cooperating with the companies. So we are interested in getting these research projects. And then if they want to have real problems solved, sometimes the companies are really desperate and they need help, then they also have to pay for it. For example, I mentioned this company with the cooking pots. We told them, okay, bring us a cooking pot so that we get an impression. They come with a truck. In this truck, something like 500 cooking pots, and they tried everything. They filled it with concrete to investigate the vibrations. They made all kinds of changes with milling tools and so on. And suddenly we had 500 cooking pots in our institute. Therefore you can see there was really a pressure for them to solve this problem. And this gives the right atmosphere to cooperate, to work together on the same level. This is always important. We want to talk to them on the same level. Not on the level we know how everything works and we tell you now. This is not what we want to do. And we also not want to have them, we are producing sophisticated products and now let's do some academic stuff. No, we want to be on the same level. And therefore we are mainly interested to work with industry on projects on this project level and same level. But then, of course, very often we can see, oh, there is a nice test bed, there is a nice experiment in the company, and then we ask them, can we get this for our education? Can you help us to set up something like this? And then also many student theses are involved with industry projects. So in this sense, it is interesting for everybody, but only in the second phase when we have a mutual understanding. It's the same everywhere. It's the same here also in your country. When you want to work together with somebody, you must make a connection with these people. And if you are connected, if you understand each other, if you trust each other, then the other things are much easier. So sometimes I think, are you really allowed to tell me about these things because it's too secret? No, they are not allowed to tell me about this, but they can trust that I never talk about this, and vice versa. Sometimes I tell them the solution of a problem before they even paid us money or so. And this is the kind of trust you must develop. And then if you are partners, then it's getting very interesting. So there are, for example, companies which call on maybe in October and tell me, we have some money available for the rest of the year. It is gone if we have not spent it until December. Do whatever you want. Just do whatever you want, useful, and tell us about, give you the money. And this is something you really must develop trust in the people. And at the same time, sometimes they are calling, we don't have any money available, but you have a problem, can you help us? And then of course we also help without any money. And so you must get away from asking companies, please give us a few undergraduate programs. You must become partner of the company, and then all the interesting research and money and all these issues follow. I would be highly interested to see how it works here and whether this is possible, but this is a very big difference between the countries and our approaches. The question was which kind of support is given to startups. Yes, we have in our university a certain part. It's an external company but owned by the university, a little bit strange thing. And they are supervising startup companies and advising startup companies. And they are quite successful. They had something like 60, 70 startup companies. Some of the startup companies survive and do very well. Some of them go out of business after a few years, very different. And they get a lot of advice. And as a little startup, you need especially advice. For example, we as engineers, we are not used to think in terms of money. If you want to make a startup, you need something who knows about money and taxes and salaries and legal aspects and all these kind of things. And they get this advice from there. And this is one important possibility to get support. Not money, but words and these kind of things. Then there are also possibilities to get money support. This is usually given for the first 2 or 3 years, and it should cover the initial phase of such a small company. First you have to create your product, then you have to advertise it, and there's this, it's called the valley of debt, where many companies cannot survive because they have not earned money up to now, and they only live from what they get from other sources. And there's also some money available for these. And then in the University of Stuttgart, there's another concept. It's called technology transfer centers. I also am the head of one of these technology transfer centers, where you kind of can arrange projects with industry which have no research background, which are more engineering projects. So there are different sources of support. Maybe one other word about support for students and for doctoral students, which might be interesting. Our doctoral students usually have positions at the university. So they get a salary from 50 to 100% of the regular engineering salary. And this is something you can live on. You can have your apartment, you can eat and drink and clothes and heat or whatever. You can have a girlfriend, or maybe have 2 girlfriends or whatever. So this is possible with this kind of salary. You will not become rich in this time, but this is what our doctoral students are living on for these 5 years. And for us it is important that these guys, these young women and men, can concentrate on their research. We not want them to drive taxi in the evenings or go to a restaurant and cook in a restaurant over the weekend. No, they should concentrate on their engineering work. And so the only way to do it, give them enough money that they not have to do this. And so all our research projects are funded projects, so all these people have this funding from the institute. And I have heard in here it's quite similar. I, as a professor, I'm responsible for getting this money and for looking for this money. And then the second issue is, of course, always how to find good people who are able to do these projects well. Getting the money is complicated, but I can do it. I can solve this problem. Getting persons is getting more and more difficult. Getting young people with a bright brain and interest, and so this is really the big issue. And we are always so happy when we find some clever young women or men who want to work with us and who are able to do this. And this is really the big challenge in research. You need the brightest persons you can imagine. So our rule is every doctoral student must be more clever than I am, then he's in the right category, and then we are happy with him. So that's how it works. They are funded by the institute, paid by the institute, and do this research projects tightly supervised by me and my vice directors and the other academic staff. Okay, so I do not see further questions. Further questions in the Zoom meeting? Also not. Okay, it's shaking his head. Then thank you very much for being here. Thank you very much for your interest. If you are interested to hear more about some specific projects, this Thursday afternoon I will talk about 2 projects in some detail, where I go more into the engineering things. And next week, Thursday, there will be 2 more talks about 2 different topics. So if you're interested, I would be happy to see you again. And have a nice afternoon and evening now. Bye. Okay.
Okay, first of all, I would like to thank Professor Peter Eberhard for the insightful and informative session. And I would also like to thank all the distinguished guests representing the academic staff of the University of Malta for their participation, whether in in-person capacity or virtually. And obviously the students as well, thank you for the participation. And finally, I would like to add that this is the first of series of seminars like Professor mentioned, and I would like to see you in those as well. Thank you and have a nice day.